Hello and welcome to this video. In this video, we will continue studying our mathematics. So, I have been writing this book. I have collected all the material which I have prepared. You know, this available in Algebra on my website astavakar.org. I have been live for quite some time. So, HTML has problems with math. I have to split the problems into different parts. As you can see, if you click this link, there are lots of parts. Complex numbers is in 6 parts and quadratic equation is 7 parts. So I have decided to convert this into a PDF book. This is the PDF book. You can download it. You can notice that the date is there, 2024-08, 3rd August. So on 3rd August, I had uploaded this PDF. I periodically update this, so you can download it from here, and you can if the date changes, then you should understand that it's a new PDF. So we will now study through PDF, not through these slides, because it's duplicating the effort. It's not good for productivity. So we will straight up study from PDF. So as you can see in the book, we have logarithm, progression, complex numbers, polynomials, and theory of equations. I have already made videos on logarithm, progressions, and complex numbers. These are done. We were dealing with theory of polynomials and theory of equations. And there are other chapters as well: permutation, combination, mathematical induction, binomials, multinomials, and expansion, determinants, matrices, and inequalities. Right now, I'm adding more problems to permutation and combinations. All the problems have been solved in this PDF till permutation and combinations. So you might want to skip the entire video, just download the book and start reading on yourself. These chapters I will work on, remaining 5 chapters, mathematical induction to inequalities. So please wait while the book gets updated. So continuing further from our previous video, we will continue our study of this theory of polynomials. We had covered up to Eisenstein's irreducibility criteria. Now the next theorem is extended Eisenstein's irreducibility criteria. So this theorem states that if there is a polynomial fx, which is an x to the power n minus 1, x to the power n minus 1, and so on, a1x plus a0, you know, your typical polynomial. And this polynomial has integer coefficients. Okay, so an minus 1, n minus 2 up to a1, a0, all these are integers. Now, if there exists a prime number p and an integer k, k is in the set of 0, 1, 2 up to n minus 1, such that p divides a0, a1 up to ak, but p does not divide ak plus 1, and p square does not divide a0, then fx has an irreducible factor of degree at least k plus 1. In particular, if p can be taken so that k is equal to n minus 1, then fx is irreducible. Now, what we do is we split this polynomial into two polynomials, gx and hx. We write gx as bk x to the power k plus bk minus 1 up to b1x plus b0, and similarly for h, our coefficients are cr minus 1, and so on. Now, these coefficients bi and ci will be in the set of complex numbers. Set of integers is basically set of complex numbers. Not the same, vice versa is not true though. So we have I is equal to 0, 1, 2, and so on. Bk is not equal to 0, cr is not equal to 0, otherwise the degree of polynomials will be messed up. And we have 1 less than equal to m, r is less than equal to n minus 1. Now if we multiply these two polynomials, the constant term would be b0, c0. Now we are given that a0 is divisible by p and not by p square. Therefore, only one of b0 or c0 is a multiple of p. So without loss of generality, we can assume that p divides b0 and p does not divide c0. Similarly, we are given that p divides a1. Now a1 would be, if you multiply these two, coefficient of x b0 c1 plus b1 c0. Now it already divides b0, so p must divide b1 c0. And similarly, we have already assumed that p does not divide c0, that means p should divide b1. Now we continue this. P divides a2, so it should divide b2 c0, and therefore p should divide b2. So we conclude that from this observation that b0, b1, bk are all divisible by p. Now ak plus 1 would be bk c1 plus bk minus 1 c2 plus bk minus 2 c2 and so on. This implies that p does not divide ak plus 1. Now notice that here bk is divisible by p, bk minus 1 divisible by p also, and so on. Thus it follows that b has a degree greater than k plus 1. Now we proceed into quadratic equations. Ideally I would have liked to start this in a new video, quadratic equations, but we have spent very little time on this video, so I'll just continue it further. So a quadratic equation has this form: x square plus bx plus c is equal to 0, where a, b, c are in the set of complex numbers. So this is called a quadratic equation. Now the numbers a, b, c are called its coefficients, that is coefficients of the quadratic equation. The quantity b square minus 4ac is called the discriminant of the equation. Typically it is denoted by capital D or delta. If you plot a quadratic equation, it will always show up as a parabola. Now there are certain examples here: 4x square plus 4x plus 1, so a is equal to 4, b is equal to 4, c is equal to 1. If you look at 7x cubed plus 10, then it will not be a quadratic equation because the power of x is 3. So it's a cubic equation, not a quadratic equation. Similarly, if you consider 3x square minus 2x to the power half plus 7 is equal to 0, then we don't have the term x, and we have this term x to the power 1 by 2, which cannot be there in a quadratic equation. Similarly, we have 2x square minus 4 is equal to 0, here a is equal to 2, b is equal to 0, and c is equal to minus 4. So yes, it is a quadratic equation. A quadratic equation is called incomplete if one of the coefficients b or c is 0. So the fourth example here is an incomplete quadratic equation because b is 0 in this case. An expression of the form x square plus bx plus c is called a quadratic expression, while other elements are same as the quadratic equation. If two expressions in x are equal for all values of x, then this statement of equality between the two expressions is called an identity. You will see the examples very soon. Fx is equal to 0 is said to be, and this should be identity, there is spelling mistake, in x if it is satisfied by all values of x in the domain of fx. Thus an identity in x is satisfied by all values of x, while an equation is satisfied for particular values of x. Now consider this: x plus 1 whole square is equal to x square plus 2x plus 1. It is an identity in x, okay, because for all values of x both are same. So these are identical equations. X square minus 5x plus 4 is equal to 0, and 2x square minus 10x plus 8 is equal to 0 are identical equations because both have same roots 1 and 2. Essentially, this equation you can obtain by multiplying 2 to this equation. Okay? Now we observe 2 points from this information. That is, two equations in x are identical if and only if coefficients of similar power of x in the two equations are proportional. Thus, ax square plus bx plus c is equal to 0 and a1x square plus b1x plus c1 is equal to 0 are identical equations. Then a by a1 is equal to b by b1 is equal to c by c1. An equation remains unchanged if it is multiplied or divided by a non-zero number. So essentially that was this example. An expression of the form a0 x to the power n plus a1 x to the power n minus 1 and so on, where a0, a1, a2 up to an are constant, a0 is not equal to 0, and n is the positive number, is called a polynomial in x of degree n. This we have already covered, I guess. As a special case, a constant is called a polynomial of degree 0. Now we study rational expression and rational function. An expression of the form px by qx, where px and qx are polynomials in x, is called a rational expression. In the particular case, when qx is a non-zero constant, it reduces to a polynomial because the coefficient will be just divided by that constant. Thus, every polynomial is the rational expression, but the converse is not true. So the examples are given here: x square minus 5x plus 4 by x minus 2 and 1 by x minus 7. Next topic is roots of a quadratic equation, but I think I'll stop here. In the next video, we will cover roots of quadratic equation and we'll proceed further into quadratic equations. We'll see the nature of roots and the signs of expressions and so on. So I hope you have enjoyed this video. I know it has been a long time since I recorded math videos, but I'll try to do regular uploads. Thanks a lot for watching, and don't forget to subscribe to the channel if you have not already subscribed, and press the bell icon to receive notifications from the channel about new uploads. This is not something which I need. I want you to subscribe to the channel and like the video so that others can benefit from the video, because YouTube is more likely to show this video in their feed or in searches if more subscribers are there and more user interaction is there. Thanks a lot for watching. Have a nice day.